Right, good morning all. Thank you, whoever said that. We're going to move on today. We've done the frequency response thing over the last 3 weeks and all the rest of it, so we should be now in a position where we can move on to something else. And the something else in this case is something called the S-plane. Okay, so let's have a look at what's in store today. I'm going to take a step back from all the frequency response kind of stuff. I'm going to take us back to looking a bit more at transfer functions. Okay, so we're going to have another look at what determines the performance of a system and how it's reflected in the transfer function. Okay, so if you cast your minds back a couple of months to when we first developed transfer functions, we were talking about things like time constants and natural frequencies and all that kind of thing. We're going to go back a step that way. But what I'm going to do is introduce you to a graphical technique that hopefully will make life a little bit easier. Okay? When we've got very simple systems, a simple first order or a simple second order system, it's quite easy to algebraically work out time constants and damping ratios and all those kind of things and get a feel for the overall performance of the system. As soon as the system models become a bit more complicated, it's almost a case of not being able to see the wood for the trees because you've got second order bits and first order bits and integrators and all this going on. So as the complexity increases, actually getting a kind of a gut feel and understanding of how these systems behave gets a little bit trickier. Okay. So what we're going to do is introduce a graphical technique that presents that performance in what's hopefully a bit more of an user-friendly kind of fashion. Okay. Now, for the introduction of this thing, I will be using simple transfer functions as an example. So you might be looking at it saying, well, yeah, okay, what's the point of that? It's dead easy anyway. But if you bear with me, because the big advantage of the S-plane comes in as we get more complex systems. Okay. Performance can be expressed on the S-plane. Look, I haven't actually told you what the S-plane is yet, okay, but we'll get to that. For single input, single output systems, we've developed models expressed as transfer functions. Okay, first couple of weeks of this module, that's what we did. We introduced the concept of a transfer function, and we introduced the Laplace operator S. Okay, now, the S-plane is simply a two-dimensional representation of values of S. It's got to be two-dimensional because S can be a complex number. Okay, so basically it's an Argon diagram. You've got a real axis and an imaginary axis. So the S-plane is a two-dimensional representation of space onto which we can draw values of S which might be complex. Or to you and me, it's a bit of graph paper. Okay. Right, just a refresher, transfer functions take the form of usually G as a standard letter, brackets S to show it's a function in the Laplace domain, controlled variable, which is the output, over the reference variable, which is the input. So output over input is the transfer function. None of this should be news to you. Okay. This shouldn't be news either, really, in the point being that the dynamic behavior of these systems, okay, can be determined directly from the transfer function. Okay. If you cast your mind back to the start of the module, we could develop transfer functions based on the differential equations of motion, or, you know, if it's maybe an electric circuit, it's a differential equations describing the current flow. So we can generate transfer functions, we can generate system models. Once we've got those models, we can then determine the dynamic behavior from those transfer functions. Okay, so for example, with a simple system, we'll be describing that dynamic behavior in terms of a time constant if it's a first order sort of thing, or perhaps as natural frequencies and damping ratios if we're talking about second order. So as soon as we have the transfer function, we can say something about the performance. I'm going to start off gently. Okay, so note that a lot of the information that we've been dealing with, 'cause at a fairly basic level, is actually held in the denominator of the transfer function. Yeah? So if you think the standard form for first order is 1 over 1 plus tau s. So that tau, which tells us about the dynamics of the system, is in the denominator. Similarly with a second order system, if we model a second order system, comes out as 1 over 1 plus 2 zeta omega and all the rest of it. All the information is in the denominator. Okay? We haven't really discussed the effect of S terms in the numerator very much. We know they can exist, but in real physical systems, we tend to find all that information comes into the denominator of the transfer function. Okay. If we look at any transfer function, let's work around a simple first order 1 over 1 plus 1 over 1 plus 5s. Okay, just for the heck of it. If we look at the denominator of that transfer function, 1 plus 5s, you could imagine immediately there's a value of s that makes that denominator equal to 0. Okay, what is it? If I had 1 over 1 plus 5s, what value of s will make the denominator 0? Minus 1/5, absolutely. Okay, and if the denominator is 0, what happens to the overall transfer function? Something over 0. It's infinite. Okay, so the key point being there are particular values of s that will make my overall transfer function infinitely large. These values of s are referred to as poles. The system has as many poles as it does powers of s. Okay. Go back to my little example, 1 over 1 plus 5s. What's the time constant for that system? One over 1 plus 5s. What's the time constant, tau? No, 5 seconds, I think somebody said. Yeah, 1 over 1 plus tau s is the standard form for a first order thing. So the pole is at minus 1 over the time constant. Okay, the point I'm trying to make is that there's a relationship between the value of the pole and the dynamic performance of a system. If we've got s terms in the top, in the numerator of the transfer function, logic suggests there are also values of s that will make that numerator equal to 0. Okay, in just the same way, there could be values of s that make that equal to 0. And those values of s, surprise, surprise, are called zeros. Okay, so if we have an algebraic transfer function, we can identify values of s that make the whole thing infinitely large. They're called poles. And we can identify values of s that make the whole thing equal to 0. And they're called zeros. We okay so far? That's the concept. Here's an example. Okay, there's an example transfer function that I made up this morning. You can see from that if we make s equal to minus 10 or s equals minus 0.2, we will have an infinitely large value for that transfer function. Okay, s equals minus 10, pop it in there, that becomes 1 minus 1, which is 0, times the other brackets, it's still 0. And similarly, if we make s equals minus 0.2, that's the one related to this part of the transfer function, and again, we'll get an infinite response. Okay. And they're the system poles. And as you can see from looking at the shape of that, they're strongly related to the time constants associated with that system. In other words, if we know where the poles are, we know what the time constant is. In other words, we understand the dynamics of that system. In the same way, looking at the numerator now, if we made s equal to minus 1/3, it would make the numerator equal to 0, and hence the overall transfer function becomes 0 as well. That's a system 0. Okay, so we can come up with these values of s that do particular things to the transfer function. Okay, they either make it infinitely large or infinitely small. And this is where the s, I'm getting there eventually, I'm getting to the s-plane. We can portray the position of those poles and zeros graphically on the s-plane. Okay. The s-plane is a complex plane because s can take complex values. And because the pole positions are related to behavior, if we have a piece of paper, a piece of graph paper in front of us showing where the poles and zeros are, that helps us to understand the system behavior. Okay. That's the theory. Does it make sense so far? Okay, we've got these things called poles, and they're somehow related to, well, in a first order sense, they're related to time constants. If you look at the behavior of a quadratic or a second order system, and you look at where the poles end up, they're also related to things like omega n. Okay, and in fact, omega n and zeta, that information comes out. So if we know where these values are, and pop them on a piece of graph paper, if we can interpret that properly, we can tell what the system performance is going to be in a dynamic sense. I've just said all this really. Note that the poles and zeros are related to the previous, related to the terms previously mentioned. So for a first order system, the pole is minus 1 upon the time constant. If we look at a second order system, okay, we will get 2 poles. Okay, and depending on the numbers inside the quadratic, I'm sure you could imagine if you were to factorize a second order quadratic, in some cases you will get 2 real roots. Yeah? So in other words, you will get 2 real poles. In other cases, you will get a pair of complex numbers. You've all factorized quite enough quadratics over the years to know what I'm on about. So if you factorize a quadratic, depending on the range of numbers, then you might get a complex solution. Okay. Point to note is that when you factorize a quadratic and you get a complex solution, they tend to appear as complex conjugate pairs. Yeah, because of the plus or minus bit in the factorization. So you'll get, when you factorize that quadratic, you'll get a real part that's the same for both roots, and you'll get an imaginary part, one of which is plus j something, one of which is minus. Okay, so they're going to appear as a pair. You get a complex conjugate pair, or you get complex solutions for damping ratios that are smaller than 1. You get 2 real roots when the damping ratio zeta is greater than 1. What do you think you get when the damping ratio is exactly 1? When zeta equals 1? Any wild guesses? Not quite, no. What you get is you get 2 identical roots. It's a perfect square. Okay. Right, system with s terms in the numerator gives rise to zeros as well as poles, and these are normally shown as circles on the plane. That's because I left out a paragraph that said when we're representing poles on the s-plane, traditionally we use little crosses. Okay, when it's zeros, circles. I'm going to be focusing a lot more on poles than zeros, by the way, so we'll... Okay, there's a bit of the s-plane. There's my graph paper. In order to accommodate all the possible values of s, it needs to be a complex plane. So I've got a real axis and an imaginary axis. And say, well, what about my example first order system? Somebody going to tell me where the pole is? which is, you can do that, 1 over 0.5. Minus 2, thank you very much. So if I was to make the value of s minus 2, my denominator would become 1 plus 0.5 times minus 2, 1 minus 1 equals 0. So that's my system pole. So it's down there. Okay, it's as easy as that. There's another one. Similar first order system, 1 over 1 plus 0.2s, you can see by the same mechanism exactly that that pole is going to end up at minus 5. Okay, I'm not going to go into the complex stuff yet. Let's just make sure that we understand when we see a pole position on this plot what it means. Okay. Which one of those two systems has got the faster response? Or putting it another way, which has got the shorter time constant? That one or that one? That one. That's faster. No, I see some shaking heads in the audience. That one's faster. This one has a time constant of 0.2 seconds. This one has a time constant of 0.5. So I would suggest that the left-hand one is the faster responding system. Okay, again, cast your minds back to when we were looking at time responses for first order systems. You remember that exponential? And it would get to 63% of the final value within one time constant and all that stuff. Well, if the time constant is shorter, that means the system is responding more quickly. If I look at the algebra of my transfer function and end up with a number of poles along here on the real axis, that tells me the response rates for the system. The further to the left my poles go, the faster my system is responding. Okay? So I can simply draw a graph, pop the poles on it, and by looking at where they are, I can tell if this system is fast or slow. So I'm starting off way on there, left-hand side, nice fast system, good response in a first order sense. As I travel rightwards towards the origin, my response is becoming slower and slower. Okay, so if you imagine perhaps something like a step response, you're getting the exponential. What do you think happens when I get there? S equals to 0. It won't get there. What transfer function do you think, what transfer function would give rise to a pole at the origin? 1 over s. Absolutely right. 1 over s would give rise to a pole at the origin. And what does 1 over s represent? It's an integrator. Okay, so by the time we get to that point, our first order sort of transient response is changing because once we hit s equals 0, what we've got is an integrator. Pole position is dependent on time constant. We've just walked through that one. And what about designing on the S-plane? Well, what we've just talked through, I mean the left-hand side of the S-plane here, all the values are negative. All the real values are negative. Okay, so on the left-hand side, starting way over here with large negative numbers, I've got, for example, a system that responds quickly. These are responses to impulse inputs, okay? So if I put in an impulse input, what happens here is I get quite a quick decay. As I travel towards the origin, my decay is getting shorter. If I did have the pole at the origin, what do you think that graph's going to look like? What's the integral of an impulse? I've lost the ability to scribble because they've swapped monitors on me. I could use this nice blank space here to make you sweat until you tell me what that integral would be. What you get here, okay, if you imagine an impulse is an unit impulse, is an input of very, very short duration. And because it's an unit impulse, it's got an amplitude such that the area under that impulse equals 1. Okay, and then the value comes back down to 0. What you'd get here actually is a step. It would go up, but it wouldn't decay at all. It would stay constant. If you have a look at what happens when you actually integrate an impulse, you should find that to be true. I'll come to the right-hand side of this picture in a minute. Okay. Some of these values you look at up there have now got a complex part. They've got an imaginary part to the transfer function. So the poles become imaginary. I'm looking at that one up there that I can't quite reach. Okay? Now, if you factorize one of these second-order quadratics to give you 2 poles and the poles come out as complex, there's a real part associated with that complex number. So in other words, there's a value along the real axis that corresponds to that complex pole. And that value tells me exactly the same as it does for a first-order one. It tells me about the rate of decay. Okay, so it's complex, so I'm going to get some oscillation, but the real value tells me about the decay of amplitude within which that oscillation is happening. Okay. The imaginary part tells me about the frequency of oscillation of that system. Okay. So the further up the imaginary axis I go, the faster the oscillation. It's related to omega n. Okay. And if you have a look at what happens when you factorize a typical second order sort of quadratic, omega n is the number that determines the value of that imaginary part of the pole. It's not equal to the imaginary part, but it's what determines it. What we actually get for that imaginary part is not omega n at all. If I was to read across the coordinates from my complex pole just there and look at the imaginary number, what that would tell me isn't omega n. It would tell me about what I call omega d, the damped natural frequency. In other words, the frequency at which it's really oscillating, which is different to omega n. The only time it oscillates at omega n is if there's no damping at all. As soon as we introduce damping, it sort of slows down a little bit. So the frequency or the number on that imaginary axis tells us about the actual frequency of oscillation of the physical system. Which is why, when you look at S-plane diagrams, that imaginary axis is usually labeled J omega, because you can read directly from it the frequency of oscillation in radians per second. Okay, omega d. How are we doing? A couple of nodding heads. This issue of the S-plane, some people struggle with this because it's really abstract. Okay, because what we're taking is we're taking a bunch of equations, which by now, you know, you've been students here long enough to understand equations and even to understand differential equations. And instead of solving them and doing the usual approach, what we're doing is simply representing those equations with kind of noughts and crosses. So all the S-plane is, it's a graphical way of representing an equation. And in our case, that equation happens to be a transfer function. So some people find that abstraction a little bit of a step too far sometimes, but you'll soon get the hang of it. All we're doing is we're representing the roots of equations as crosses or little circles on a piece of graph paper. What about this big empty space I've got over here? Just continue the story, okay? This is really fast and stable. Our system's responding. This is slowing down and stable. This is my integrator position at the origin, where in response to an impulse input, it would hop up and then stay there. What do you think happens on the right-hand side? Yeah, they grow. Instead of diminishing, they grow. And if you think about where the pole position's coming from, what that implies is that we've got a negative time constant. Okay. There's the right-hand half. And putting it crudely, if your system has got a pole in the right-hand half, your system's going to be unstable. If your poles come out negative, everything's nice, it's stable. Even if your pole's sitting on 0, we're going to get an oscillating perhaps, but non-decaying response. As soon as we move into the right-hand side of that S-plane, we can get positive poles, and positive poles gives us varying degrees. There's my integrator, actually. That belongs with that one. Varying degrees of unstable response. So, somebody gives you a transfer function, I don't know, 4th, 5th, 6th order equation. You scratch your head for a bit saying, well, I can't factorize that, so use a piece of software to do it. Factorizing high order polynomials manually is a bit of a task, so you get some software to do it. It tells you where the roots of that polynomial are, the poles, and you put them on your picture. If one of them ends up on the right-hand side of this, you think, well, I've got a big problem here, because my system overall will be unstable. Okay, and it's really quick and easy to see that. You don't have to work anything out particularly. Once you've got that polynomial factorized, you can very quickly look at the performance. Let's go back a moment. I haven't included this on the slides, but it's a worthwhile thing to know. Let's pretend we haven't got any right-hand poles. Let's go back to the previous shot. If I had a system with a number of poles in, let's say, these 3, I factorized my 3rd order system, and I've ended up with 2 real poles, and that will have a conjugate partner down here, because they always come as a conjugate pair. So that, in fact, would be a 4th order system to give me those 4 poles. Okay. Ignore the ones on the axis if you don't mind. Okay. How do I know how the system's going to behave? Because it's really giving me 3 options, isn't it? Is it going to behave slow first order? Is it going to behave quick first order? Or is it going to be behaving in a 2nd order sort of way? No idea. Okay, because what it's giving me is, if you like, it's got 3 options. It would be really useful to me if I knew which one of those was dominant. Okay, which one of those 3 slightly conflicting pieces of information I'm being given is closest to the truth. I mean, the real truth is the response is going to be a mixture of all 3, really. But does one of them dominate over the others? And the answer is yes, they do. Okay, and the way to work out which one's dominant is relatively straightforward. Just ask yourself which one's closest to the origin. Okay, and the pole position closest to the origin is the one that produces the dominant response. Why might that be? Well, if you think about it, that one, the response concerned with this one, will have decayed away to nothing while this one's still doing things. Okay? So the further left you go, those poles still have an effect, but that effect dies away really quickly. And the one that persists and lasts for longest, and hence is dominant, is the one closest to the origin. Okay? We're going to be using that as a design tool a bit later on to know how to make the performance of a system do what you want. Okay. We can use this S-plane to design system behavior. If you imagine that we've got a job, our job is to design system controllers, and we've got a design specification. The spec might say, right, design me a controller for this system such that the rise time is equal to or less than a particular time, maximum overshoot of something or the other. You're given this kind of information to design things. So what we can do is we can translate that information into space or regions on the S-plane. Okay. So let's see if we can understand, in terms of things like rise time and all the rest of it, how that translates onto the S-plane. I've put on one complex pole there. It will have a complex conjugate partner down here. But seeing as these drawings are always symmetrical because of that, we tend just to look at the top half. I said to you before that the imaginary axis is a frequency number. Yeah? And the imaginary component of that pole position is known as omega d, the damped natural frequency. And you can simply read that directly from the j-axis, j omega. Okay, the damped natural frequency happens to be omega n times the square root of 1 minus zeta squared. That will come out of the algebra. You've probably seen that before. The real part, we've looked at it for first order systems, is minus 1 upon the time constant. Relating it to second order systems is minus zeta times omega n. Okay. So we can immediately go from omega n and tau into pole positions and place our pole that way. There are some other things we can relate it to. If we're particularly interested in overshoot, for example, what bit of a second order transfer function is going to give us the clue about the amount of overshoot we've got? Bear in mind there are only two variables in the second order transfer function. Yeah, it's going to be the damping ratio, zeta. It's not going to be omega n. That tells us about the frequency of oscillation. Zeta is the one, you've done it before when we were looking at time responses. We had that standard set of time responses. You can directly relate overshoot to zeta. So where does zeta appear on the S-plane? Well, it's this angle. Okay. The cosine of that angle is zeta. Okay, down here, omega d, damped natural frequency, and cos phi equals zeta. So the angle subtended at the origin by a line drawn from the pole is the damping ratio. Okay. So if I'm turning this on its head and starting to use it as a design tool, let's say I want an overshoot of 10%. Sadly, I remember that means zeta equals 0.6. Okay, I've been doing this for too long. I would just draw myself a construction line at an angle whose cosine is 0.6, and that will represent all the possible points that will give me zeta 0.6, which is my 10% overshoot. Okay, so I've got one design constraint. I might have another design constraint, perhaps linked to the frequency, all linked to the rate of decay. And that will give me another construction line, and where the two lines meet is where I want to put my poles to give me that performance. Okay, what else can we get from this that's not actually written on the slide? Omega n's a bit lost, isn't it? Because it's combined with other things. We can work it out from there or perhaps from here, but it's a bit lost. Not written on the slide, but if you look at the geometry of this thing, it's just a triangle. The length from the origin directly to the pole is omega n. Okay, so we can pick up omega n very easily as well. Does that make sense? Well, let's have a look at a few things. If I decrease the damping, in other words, I make zeta smaller, what's going to happen to my pole position? Which sort of direction do you think it's going to move? I keep everything else the same omega n, but if I make zeta smaller, what do you think is going to happen to that pole? That way? Just level. It will be in an arc, absolutely. Okay, don't know if that's what you meant. I saw the hand signals, but if you take on board what I just said, that this dimension from here to the pole, the radius, if you like, is omega n. If that's unchanged, but I'm changing zeta, that pole is going to move in an arc, clockwise as it happens, because as I make the damping ratio smaller, this angle will get bigger. Where does it end up when the damping ratio equals 0? Missed that, sorry. Somebody offered a suggestion. When the damping ratio equals 0, where has that pole travelled to? It's moving clockwise in an arc. When zeta equals 0, what's that angle? What's got a cosine of 0? 90 degrees. So by the time we get to zeta equals 0, that pole is actually going to be sitting on the real axis. Yeah? And surprise, surprise, we then see that omega d, or the imaginary part, is the same as omega n, which is perfectly okay because there's no damping. Okay? What happens if I increase that until zeta equals 1? In other words, I'm putting more damping into the system. I think we've already determined that my pole travels in an arc, and the radius of that arc is omega n. If I make zeta bigger until it's equal to 1, where do I end up? On the real axis. Yeah, it moves around anti-clockwise until, well, when zeta equals 1, what's got a cosine of 1? 0 degrees. So we end up on this real axis. Zeta equals 1, if you recall, represents critical damping, which has got no oscillation. Okay, and our pole has been pulled down onto this axis, which is really the same place as a first order pole would be, and the behavior is really linked to first order sort of behavior. Let's not lose track of the one that's down here. Okay, there's a complex pair. And what happens when these move round is you get both of those. One comes up from beneath, one comes down from above, and you get both of the poles in the same place. So effectively, you've got two first order poles sitting on top of each other. There's a load of things. There's way more we can get from the S-plane. And once you get comfortable with it, it's very, very easy to get that information just by looking at the shape of the picture. So what we've got here, omega d, omega n, time constant, those kinds of relationship. Let's go back a minute before we do that. I've got a few minutes. Always seem to finish these too early. I'm sure you hate that. what else can we do with this thing? Well, I've ascertained already how to make one particular set of poles dominate the response of a system. I can express that in terms of zeta, in terms of omega n, in terms of tau, all those sort of dynamic things that I understand. And we've briefly touched on using this as a design tool. Now, the trouble with that is that in terms of design specification, we tend to talk about things like settling time and rise time. Okay, cast your mind back a few weeks when we were talking about those terms. Anybody remember what settling time is? No. That's right. It's the time taken for a system output to come within a certain percentage and stay within that percentage of the final value. And the definition for settling time, you might recall, there are multiple definitions. The one that I tend to focus on when I'm chatting to you guys is the one where the output gets to within 5% and stays within 5% of the final value, the time it takes to get to that point. Do you remember what that was defined as in first order terms? Yeah, the time taken, after one time constant, our system gets to 63%, our first order system gets to 63% of the final value. Yeah. How long does it take it to get to 95? Do you remember? This is our definition of the 95% settling time. No, maybe not. It's too long ago. That's okay. I'm going to get you with this one because this week's tutorial sheet is a revision one. Okay, you'll have to look back through your notes. 3 time constants. Yeah, if you recall first order responses and the definitions, after 1 time constant, the system will reach 63% of the final value. After 3 time constants, it's 95%. And what's the other definition of settling time that we discussed? Yeah, 5 time constants, which is something like 99.5% of the final value. Okay. So if I'm given a specification in terms of in terms of settling time, it's very easy to relate it to somewhere on this real axis, because this real axis is all about settling time. Okay. So I can it's all about tau, beg your pardon. So I can relate this real value just as easily to settling time. Okay. The other performance definition that we used was a thing called rise time. Yeah. Yeah, I'm going to ask you again. Anybody remember what rise time is? No, that's closer to settling time, I'm afraid. Yeah, the time it first reaches, or within a particular percentage of the desired value, regardless of whether it then oscillates beyond or underneath that. Okay, so the time to first reach that value, we tend to define it as to go from 5% to 95% to cut out the sort of flat bits at either end. But it's roughly that. If you think of an oscillatory system, that definition of rise time is approximately 1/4 of a wavelength. Okay, if you think of it as a sinusoid, starting at the bottom, thinking of step responses, it's 1/4 of an oscillation is roughly that rise time. We'll go into this in more detail next week. And that means if I know the frequency of oscillation, omega d, I can relate that directly to rise time. Okay, so not only can I determine the required pole positions using omega n and zeta and tau and all those things, I can also do it using, if you like, the more normal commercial design parameters of rise time and settling time. Okay, so using the S-plane as a design tool to decide where you want the poles to be is actually quite straightforward. Right. what do we know? What's going on? We know that the information about the dynamic behavior of systems is contained in polynomial equations expressed as a transfer function. Okay? By plotting the values of S that give me poles and that give me zeros, we can determine the system behavior quite easily from a picture. It's a graphical way of looking at it. We can do a whole lot more with this technique, which I'll go further into next time. Okay? But really, this, if you can get your head into the idea that representing polynomial equations as noughts and crosses is actually okay, as an abstract way of presenting them, then this then becomes really easy. Because as human animals, we're all actually very good with visual symbols. Okay? So that's an introduction to poles on the S-plane. You'll notice, by the way, that I've cunningly ignored zeros at this stage. Okay? And the reason, and that's fairly deliberate in that all the things that we've tended to talk about up until now, time constants, overshoots, all those sorts of things, that information is contained primarily in the denominator. I'll come back and talk to you about zeros next week or the week after. Okay? But for now, if you let me off the hook, that'll be handy.